Right. Introduction. Before entering into the modeling of electric vehicle, first let's see the common difference between the conventional vehicle and the electric vehicle. Okay, right. So look at the table. In the table, in order to store energy, fuel tank is used in conventional vehicle. Okay, whereas battery is used in case of electric vehicle, right? And then in order to fuel or in order to energize the vehicle, you need fuel pump in case of conventional vehicle, and you need a charger in case of electric vehicle, right? And then in order to make the vehicle to move, you need a fuel engine. Okay, you need a fuel engine in case of fuel vehicle, and then you need an electric motor in case of electric vehicle. Okay, so this is the most important difference. Okay, right. The next one, in order to control start, stop, and speed and acceleration, you need a carburetor in conventional vehicle, and you need a controller in case of electric vehicle. Okay, in electric vehicle, right? In order to provide power to the accessories such as radio, light, air conditioner, you need an alternator. Okay, in case of fuel vehicle, and in electric vehicle you need DC to DC converter because all the accessories works on DC power supply. Okay, since battery stores energy in the form of DC, you need just a step down or step up DC power supply. Okay, most probably step down DC power supply is necessary, right? Then in order to, if you use an AC motor in electric vehicle, then you need an DC to AC converter because um, battery stores DC power, and when your AC motor needs AC power, then DC to AC converter plays a major role, right? So these are the most common difference. And here you can see from the picture, you can see the most important thing is that you need a fuel tank and an engine in case of conventional vehicle. Okay, even though if it is a bike, okay, you need these two. Okay, a fuel tank and an engine. It may be a diesel engine or it may be a petrol engine. Okay, these are the two things we will look into it. Okay, when we buy a electric, when we buy a car or a bike. Similarly, when you go to electric car or an electric bike, then you have to look into the motor and the battery. Okay, the capacity of the battery as well as the capacity of the motor. That is what we are going to design in this video. Okay, how how to design or how to size a motor, and then how to size a battery, and what are the other factors to be considered while designing this, while sizing the motor and the battery. So those are the things we are going to look into it. Okay, to model or design an electric vehicle, first we need to find the propulsion power. Okay, the propulsion power is calculated using the formula. Propulsion power is equal to total tractive force multiplied by the velocity of the vehicle, right? So this is the formula for calculating the propulsion power. Once we calculate the propulsion power, then we can easily calculate the size of the motor. Okay, and once we calculate the size of the motor, then easily we can calculate the capacity of the battery required to power the motor. Okay, so these are the simple steps in modeling or the design of electric vehicle. Okay, tractive forces. Tractive forces is defined as the force acting on the wheels of the vehicle. Okay, and it is the force used to generate motion between the body and the surface. Okay, between the body and the surface. And the total tractive forces includes rolling resistance force, which is denoted by FRR, aerodynamic drag force, that is F suffix AERO, then hill climbing force, F suffix HC, acceleration force, that is F suffix XI. And there are two types of acceleration force. One is linear acceleration, and the another one is angular acceleration, because the vehicle you have to turn at an angle, therefore angular acceleration force is also considered. Okay, so these all forces are together called as tractive forces. Okay, rolling resistance force. Rolling resistance force is defined as the force resisting the motion when a body rolls on a surface. Okay, so like there are different types of surface. So the rolling resistance force varies based on the type of surface. Like you see, when a wheel rolls on a concrete or a rolled gravel or an unpaved road, then the resistance will differ. Okay, so that factor should be considered. Okay, so the rolling resistance force can be equated as FRR is equal to mu RR multiplied by M multiplied by G, where mu RR is the rolling resistance constant that depends upon the type of the type of the road. Okay, type of the road, like concrete, rolled gravel, tar type road, then unpaved road. If it is a field, that will be the highest resistance. Okay, right. Then here comes the mass of the vehicle in kg, in kilogram. Okay, so m is the mass of the vehicle, so total weight of the vehicle in kilogram. Then g is the gravitational acceleration constant. Okay, that is 9.81 meter per second square. So this is the formula for calculating the rolling resistance force. For example, if you consider a field type road, then you have to use zero point 0.1 to zero point 0.3 as mu rr. Okay, then you have to calculate the mass of the vehicle, and then you have to replace 9.81 meter per second square in place of g. Okay, right. Aerodynamic drag force. It is a force on an object that resists its motion through an air, that is called a drag. Okay, so here it is the force due to air that resists the motion of the vehicle, we can say like that is called aerodynamic drag force, which is due to the air. Okay, and drag is a force that acts parallel to and in the same direction as the airflow. So that is called as the drag, and this aerodynamic drag increases with the square of the speed. Okay, that you can see the formula, where aerodynamic force is equal to half rho CD A V square. V is the velocity, that is the speed. So here aerodynamic drag increases with the square of the speed. So v square means square of the speed. So let's see one by one. Okay, so rho is the air density in kilogram per meter cube. Generally it will be 1.27 kilogram per meter cube. Okay, that is the, under normal circumstance, this will be the air density. And capital A is the frontal area in meter square. So while designing the vehicle, if the frontal area is high, then appropriately the consequences will be faced, like the drag force will be increasing. Okay, all right. Then CD means drag coefficient that varies from 0.25 to 0.45. Okay, and the final v is the velocity of the vehicle, and it should be represented in meter per second, right? So that is the formula for calculating aerodynamic drag force. And here you can see that if it is a flat plate, the CD will be, the drag coefficient will be 1.95 if it is a flat plate, because it covers most of the area, and the drag will be drag will be higher, therefore it is 1.95. It is calculated as 1.95. If the frontal area is hemisphere, then CD will be 1.42. Okay, 1.42, right? There are two types of hemisphere. So you can see, if it is facing like this, and when the airflow is towards this hemisphere, then it is 1.42, and if it is in the other side, you see it is reduced, it is 0.38. And if it is an airfoil, then it is the minimum drag coefficient, which is 0.007. So that is how some of the bodies are designed. And you see why most of the cars are like this, it is because of this drag coefficient. Hill climbing force, it is the force due to the gradient. Okay, sometimes if you want to move your vehicle in a hill station, to a hill station, then you have to consider the gradient. Okay, right? The hill climbing force can be calculated by using the formula FHC is equal to m into g into sine theta, where m is the mass of the vehicle in kilogram, g is the gravitational acceleration constant, that is 9.81 meter per second square, sine theta is the angle of gradient in radian per second. Okay, so this mass of the vehicle, it includes both the curb weight as well as the weight of the passengers inside the vehicle. So it is the total mass in kilogram. Okay, right? So this is the formula to calculate the hill climbing force. Acceleration force, there are two types of acceleration. One is linear acceleration. So linear acceleration means you can move straight, you can move either forward or backward. Okay, so this is the linear motion. And when it comes to angular motion, you have to turn right, you have to turn left. Okay, so that comes the angular motion. So these two factors to be considered. And for linear acceleration force, the formula is F is equal to m into a, that is mass into acceleration due to gravity. And in case of angular acceleration force, you have to use this formula. F omega a is equal to I g square a divided by r square eta into q. Okay, I is the moment of inertia, g is the gear ratio, then a is the acceleration, r is the radius of the tire, and nq is the efficiency of the gear. So you have to calculate all these factors for this acceleration force. Right. So now we can calculate the total propulsion power. Okay. So we know that the total propulsion power is total tractive force multiplied by the velocity of the vehicle. So the total tractive force is the sum of rolling resistance force, aerodynamic drag force, hill climbing force, linear acceleration force, angular acceleration force. So when you add all these forces, then you can calculate the total tractive force, right? Now let's assume a flat surface, and neglecting the hill climbing and acceleration force, then simply we can calculate the total tractive force in terms of rolling resistance force and aerodynamic force. Okay, because when you assume flat surface, then the hill climbing force will be zero. If you are not going to climb a hill, then again the hill climbing force will be 0, and neglecting the acceleration force, which is of course very small. If you put acceleration force is equal to 0, then linear acceleration and angular acceleration force will be 0. So FTE, total tractive force, can be calculated as the sum of rolling resistance force plus aerodynamic drag force. Okay, so these are the two formulas for calculating the rolling resistance force and aerodynamic force. When you calculate these two, then you have to multiply it, we have to multiply by the velocity of the vehicle. If you want to design a vehicle which runs at 20 km per hour, then you have to multiply accordingly, right? Right. Let's choose a sample data for designing electric two-wheeler, right? The first parameter is the weight or mass of the vehicle, that is 100 kg. So this mass, let's say that 40 plus 60. 40 is the curb weight. Curb weight means without an occupant. Okay, the weight for manufacturing a vehicle. And if you add an occupant of 60 kg, then the total weight will be 100 kg. Okay, so this is just an assumption. Okay, so we are going to design a vehicle of 100 kg that can move a weight of 100 kg. Um, that is what we are going to design, and this 100 kg is the total weight of vehicle as well as the occupant. And if the weight goes above these, then the motor will face difficulty in moving the body. All right, okay. Then let's consider the as 1 meter width as 1 meter. Then let's assume the height as 1.5 meter. Then the rolling resistance constant mu rr is equal to 0.02. So this is the rolling resistance constant for, I think, the rolled gravel, the road made up of rolled gravel, right? Then let's assume the air density as 1.25 kilogram per meter square. So normally the air density varies from 1.2 to 1.29, that is 1.3. So let's assume 1.25 here. Then let's assume the drag coefficient as 0.3. Okay, that is the usual drag coefficient in a sedan type car. That is we are also using the same for the two-wheeler. Then let's use the gravitational force, which is 9.8 meter per second square. Then the speed in kilometer, let's assume 20 kilometer per hour. Okay, and this should be converted to meter per second. We will do that later. Then the frontal area, let's assume the frontal area as 1.5 meter square. Area means if it is a rectangle, you see width is 1, height is 1.5, then the area will be 1 into 1.5, 1.5 meter square. Okay, so that is the frontal area. So now we need to calculate the velocity in terms of meter per second. So you have to convert kilometer per hour into meter per second. So how can we do that? So if it is 20 kilometer per hour, we need to convert into meter, right? So 20 into 1000 will be meter, and it is in hour, so you need to convert it into seconds. So an hour contains 60 minutes and each minute has 60 seconds. So 60 minutes times 60 seconds. So if you do like that, then you will get meter per second. So let's cancel the zeros. So it's just 200 divided by 6 into 6, 36. So which is approximately 5.5 meter per second. So that is what it is captured here. 5.5 meter per seconds. Meter per second. Okay. So now we have converted kilometer per hour into meter per second. Right. Okay. So let's calculate the total tractive force. So in order to calculate the total tractive force, first you have to calculate rolling resistance force. Okay, so we have to calculate F or rolling resistance force, which is equal to mu r multiplied by mass multiplied by acceleration due to gravity. And this is the rolling resistance constant, which is 0.02 multiplied by what is the mass, which is 100 kg. Then this one is 9.81 or 8 meter per second square. So when you multiply all these, you will get 19.6. Okay, so you will get 19.6. Right. Then next one, you have to calculate aerodynamic drag force, which is given by the formula 1 by 2 multiplied by air density, that is rho, then drag coefficient CD, area, okay, frontal area, then velocity square. So 1 by 2. So we have assumed the drag coefficient as 1.25 multiplied by CD. CD is the drag coefficient, which is 0.3. Then area is 1.5 meter square multiplied by what is the velocity, 5.5 square. Okay, so if you calculate, you will get approximately 8.51 or 8.6, 8.51 or 8.6. So that is what captured here. Okay, so the rolling resistance force is 19.6, aerodynamic drag force is 8.6. So if you add, then you will get 28.2 Newton meter per second. That is the total tractive force. So which is captured here, total tractive force. Okay, so if you want to calculate the total propulsion power for this 20 kilometer, for the speed of 20 kilometer per hour, that is 5.5 meter per second, then what you have to do, you have to just multiply this total tractive force to the velocity of the vehicle. So if you multiply, so you see total propulsion power is equal to total tractive force FTE multiplied by velocity of the vehicle. So 28.2 multiplied by 5.5. So if you do, then you will get 157.114 Newton meter second. Okay, so 1 Newton meter per second is equal to 1 watts. Okay, so 157.1 watts. So we can say 157.1 watts, but you can round it off. Okay, so you won't get a motor with 157.1 watts, but you can get a motor of 250 watts. Okay, 200 watts, 250 watts, so that even if the weight is little bit higher, even if the weight is little bit higher, like if it is 110 kg, still this 250 watts motor can drive the vehicle. Okay, or if there is a change in these parameters like a drag coefficient, if the drag coefficient is increased in real time scenario, then this 250 watts motor will manage. Okay, so it is always better to choose somewhat higher rating compared to the calculation what you got. Okay, so this is the sample data and the calculation. Right, so now we are going to calculate the capacity of the battery. Okay, so the what is the rating of the motor? So you see the motor is 250 watts. That is what we have calculated and we have concluded, right? So if it is a 250 watts motor, let's consider three cases for choosing a battery. Okay, because it depends on the voltage. In the market we can get 12 volt battery, then 24-volt battery, then 36-volt battery, and it goes on. 48-volt battery is also available, but for this small size motor, we can choose these three cases. Okay, and we know the power. Okay, 250 watts, we know the voltage. Then we have to calculate what current is equal to power over voltage. So 250 over 12 volt. If it is 250 over 12 volt, then what is the value? 250 over 12, it is 20.8. So we can approximately we can say that it is 21 ah ampere hour. Okay, if you choose 24, then the current will be 250 over 24. If it is 250 over 24, 250 over 24, then it will be approximately 10.42 ah. Okay, and if you choose 36 volt, then 250 over 36. So 250 over 36, you will get 6.94 ah. So for a 250 watts motor, you can choose 12 volt 21 ah battery, or 24 volt 10.5 ah battery, or 36 volt 7 ah battery. So this is how you can choose a battery um, for achieving that 20 kilometer per hour. Okay. So finally, we can conclude that for for a 100 kg electric bicycle or electric bike, you need to get 250 watts motor, and then you can have 24 volt 10.4 ah battery, and if you use this, the vehicle will travel 20 kilometer in 1 hour, and the surface should be very flat. Okay, these are the two assignment you can try. The first one is find the total power required to drive a vehicle mass of 100 kg at a velocity of 20 kilometer per hour with a hill climbing angle of 10 degree. So it is the same calculation, but you have to add hill climbing force, because the gradient has been given, which is 10 degree, and you have to convert it into radian per second, and then you have to calculate the total power required. Once you calculate the total power required, then you can size the motor as well as battery. Okay, this is the first question, and the second question is find the total power required to drive a vehicle whose weight or mass of 300 kg at a velocity of 40 km per hour. Consider the total force as FRR plus FAD. So here the hill climbing force is neglected. Okay, so these are the two questions that you have to do. Um, and this is the expected answer for the first assignment. You should get the power of 945.2 watts, and for the second question you should get the power of 1039 watts. Okay.